So we've been working on solving systems of equations using various methods. And the last thing we need to do to wrap up this study of systems is to talk about some special cases. So thus far, we've been looking at systems that have a solution, and that solution is the place where on the graph the lines of those equations would meet, and at that place the x and y values are the same for both equations. So if these are two equations, then x equals 5, y equals 5 would make both of those equations true. However, sometimes, much like when we had equations in one variable, when we have a system of two equations, we can also have some situations where we have no solution. And when that occurs in a system is when the two lines are parallel. So for example, if we have y equals x and y equals x plus 5. So those lines have the same slope, 1, but they have different y-intercepts. So this line is above that line. And what that means is that they will run parallel to each other forever and ever and never cross. So what that means is that there's never a value of x and y that would make both of those equations true. And we can tell from the equations that two lines are parallel when they have the same slope but different y-intercepts. So for example, I could put this line anywhere and it would still be parallel because the slope is the same. So when we're looking at a system, what are some things that can help us determine that the lines would be parallel and therefore have no solution? So the first thing I can do is just look at the equations, and I can see that here, they're both in slope-intercept form. They both have a slope of 3, but a different y-intercept. So I could tell just by looking that those two equations do not have a solution as a system. Let's say, however, I didn't notice that and I set about solving. So this system would lend itself well to substitution. So let's say I start solving. I'm going to set y equal to y. So 3x plus 1 is equal to 3x minus 3. And when I solve it, I end up getting 1 equals negative 3, which is never true. That's an untrue statement. So therefore, there is no solution to the system. And sometimes we may notice before we get to a final solution that's not true. So for example, here, if I rearrange this equation to be y equals negative 5x, and then I set the two y's equal to each other, negative 5x minus 2, negative 5x. So I know from my earlier work with equations that that's going to turn out to not be possible because there's no way that negative 5x minus 2 can be equivalent to negative 5x. So we know that that also has no solution. So what might this look like if we're solving using the elimination method and we have two equations that are both in standard form? So if I were to solve this equation, I would probably multiply this top equation by 2 and leave the second equation alone. So I can see here I have 4x plus 2y equal to 10, and I also have 4x plus 2y equal to 0. And if these x values and y values are the same, there's no way that this can equal 10 and simultaneously equal 0. So we know here we have a system without a solution. And indeed, if I solve it by subtracting the bottom one from the top one, I get 0 equals 10, which is obviously not true. So to sum up, if we end up noticing that the equations have the same slope, but a different y-intercept, we know there's no solution. If we solve by substitution and we end up with an untrue statement, or a statement that can't be true, we know there's no solution. And if we're solving by elimination and we end up with two equations equaling to different totals, we know also there's no solution. Now, just one reminder here that we oftentimes get mixed up when a solution is 0 versus when we have no solution. So remember that it's completely possible that we get a solution of x or y equal to 0 when we solve a system of equations. So let's say in this particular case, I decide to solve by elimination. So I multiply that top equation by 2, and I'm going to leave that equation the same. And then I'm going to subtract the bottom equation from the top equation. So 2y minus 2y equals 0y. 4 minus negative 6 is 10. And 8 minus 8 is 0. So the fact that 0 times y equals 10x does not mean there's no solution, because 0 times y is just 0. And that means that x would have to be equal to 0 in that case. So the solution to this system would be 0 for x, not no solution. So if you're not sure, carry it all the way through to the end, and remember that it is possible to solve for x or y equal to 0 in any case. Our second special case is when we have a system of equations with infinite solutions. And the way that we can have a system of equation with infinite solutions is if the lines are the exact same line, because that means they would have all of the same points. And so we discussed earlier in the context of solving a different problem that if we multiply all the elements of an equation by the same number, we create an equivalent equation. So let's say we multiply this whole equation by 2. So 2y equals 2x plus 4. So now you'll notice that the purple line is the same line as the green line. So every point that makes the purple line true also makes the green line true because they're the same line. And therefore, the solution to the system is that there are infinite solutions because every single point is going to be in both equations. Remember that we need to multiply the entire equation or divide, but not just the right side. So for example, if I multiply the right side of the equation by 2, I do not get an equivalent equation. I also need to multiply the left side of the equation for that to happen. So how might we identify systems with infinite solutions when we're given the equations? Well, first of all, we might just notice, oh look, this equation's been multiplied by 2. This equation's been multiplied by 3. This equation's been divided by 2. And then we know that there will be infinite solutions. But if you're not sure, or you just happen not to notice, as you're solving, something interesting will happen as well. All right, so here's my system I'm going to solve by elimination. Let's multiply the top equation by 6 so that we can eliminate the x's. So that would be 12x minus 24y equals 60. Negative 12x plus 24y equals negative 60. 12 minus 12, or plus negative 12, is 0x. Negative 24 plus 24 is 0y. And 60 plus negative 60 is 0. So nothing plus nothing is nothing. So we get a statement that is always true. So no matter what, it is in fact true that 0 equals 0. And therefore we know we have infinite solutions. So when we have no solution, we get an untrue statement. And when we have infinite solutions, we have a statement that is always true. So it could be something like 0 equals 0. It could be something like 3x equals 3x, because that will always be true. So we're looking for a statement that is always infinitely true, and that's how we know we have infinite solutions. So now as we're working with these systems of equations, we have three options. We can have a system with one solution, and we might find that by graphing or substitution or elimination. We might have a system with no solution, a parallel line. And if we identify that at any point in the process, we can just write a sentence explaining our reasoning. And we can also have a system with infinite solutions, so two lines that are the same. So if I get to this point, I can just state infinite. If I realize it at some point through the process, again, I can just write a sentence that explains my reasoning, how I know there are infinite solutions.